Okay, so let's start off where we left off last video. As I said before, today I want to continue with creating our bounding box. And what is our bounding box? Well, this is just in our Quadtree. This just represents a square. Okay, so this represents a square, and there's many ways of implementing this. And you might want to have 4 vectors that each vector represents one line, one side, or vectors that represent the left side of the square, or right side of the square, and so on. But actually, today what we're gonna do is we're gonna say private var center. I will explain it in a second. And private variable half length, and then we're just gonna initialize it. Okay, so what is this? So it just says, hey, in the middle of my square, I want this center to be saved here, and the distance from the center to one of the sides in our square is half length. Okay, so we have a square that is where each side is size 10, then the center is, let's say, 0 0, and the half length would be 5. With those two properties, we can generate new smaller bounding boxes by just moving the center a certain distance, and the certain distance is half length, or is dependent on half length. So for example, if we have a square, well, let me pull up this chart, this drawing here. Let's assume we have a bounding box that describes the square here, where this A is, and we want to split this square into 4 other squares like this. So what do we do here? How do we describe this upper left square, for example? Well, we just move the center mass, the center position to the upper left. And how do we do that? We subtract half length divided by 2 for the x value, so we move it like this to the left, and add half length divided by 2 to the y value, so like we just move it up, and that would be the center for our upper left corner square. And we just do this for every other square here, and that's simple. So let's try to implement this. We'll just call it southwest. So those functions that I write now represent a specific square in our existing bounding box. So by calling this, for example, every time, you make the bounded box smaller and smaller and smaller. Okay, I'll type in as a comment subdivides this bounding box and returns the southwest bounding box, and we'll just call new center equals center dot minus vector half length divided by 2, and also here half length divided by 2. Right, and then just return a new bounding box here, center, and then half length divided by 2. So what is this? I'll explain it for this, and then for the other ones you should know. New center, sorry. You should get an idea of how it works. Okay, so here we call minus. Okay, so let's assume again we are here in the middle, and we have a half length of this size, and we divide it by 2, so that's only the half of it. and then we subtract this length divided by 2 for in our x value and our y value, and then we end up here in the bottom left, or let's say here in the bottom left here, with our new center and our new half length that is now describing this length. And now we do this for every single square. I'll just copy this so it then call northwest, southeast, and northeast here. Now we just have to change it. This last one is pretty trivial. This last one is plus instead of minus here, but the other ones are need more stuff. So called plus here, don't forget plus. And I will introduce another vector, add vector, because this one is not so simple, because we have to change because the first and last one are simple because you just change the x and y value to the same values, but for northwest and southeast you have to change, for example, x, you have to subtract x and add to y, and vice versa, and this is not possible with our simple way of adding vectors. So we introduce another vector where we accomplish this exact feature. So we call here half length divided by 2, and call here half length divided by 2, and then we just call add vector here instead of this. And now we just do this, we'll do the same right here, but now we're just vice versa and call add vector here. Okay, that's how you do this, and we'll just copy paste the code, the comments here for the north east bounding box, for the southeast bounding box, and the northwest bounding box, right? Okay, so now we are able to create our new divided space, and now there's something a little more complicated I want to show you. So now what we want to do is, when we insert a body into our quadtree, we have to know in which square, in which quadrant this body falls into, right, based on its position. So if it's like this A here at the upper left corner, of course it has to go into the in the subtree of the northwest bounding box, right? It has to go into the northwest bounding box, and that's where we add it. And we have to figure out how that works, or how we can do this. Let's just call this quad position, and then for our position here, called fourth position, and return an int, because this int will represent our index or the position. Now let's just call it like this, just some simple stuff. Now this is going to be a little more complicated. What you can do is, you can do if conditions, if the center of x is bigger, if the x position here is bigger than the x position of our center, and if the y position is bigger than the y position of the center, then it's in the northeast quadrant, right? But that would take a lot of if conditions, and it's not very clean. But what we can do is we can use bitwise OR operation. Let me show you. Might look weird at first, as I said before, this is not a beginner tutorial, so we will be using some advanced techniques here, okay? So what is this? You might ask yourself. What is that? Looks weird. Okay, if you don't know what bitwise OR operations are, or what OR operations in general mean to binary numbers, then please read it up. It's important to know, but I'll explain it anyway here. Let me pull up this and say comment here. Returns the index in which this vector, or in which this vector bounding box index in which this vector falls into. Okay, so what is this? You do an OR operation with 2 and OR operation with 1 and then assign it again. That's weird. Okay, so let's take a look at this little chart I made. So we've got 4 children, right? And the x and y values. If there's a minus, it means the x value of this child here is less than the x value of our center. So we always have the center as our point of view. If the x value of a child is plus, that means it is larger than the center x value, and the same is for the same applies to the y value. So you can see a pattern here. If you know how binary addition, if you know how to count in binary, you know that this actually looks like how you would represent a binary number, right? Or how you would count a binary number. So this might, for example, be 0. This is 1. So if a plus could represent a 1 and a 0 could represent a 0, so that would be 0, that would be 1, that would be 2, and that would be 3. Exactly like it says here. So we can take a fact of this by saying, hey, if the position of x is bigger than center of x, we'll say 0 OR operation with 2. What does this mean? Let's go here and say 0 0 and 1 2. So that's 2 and that's 0, and our OR operation will result in 1 0 because we take every single spot where 1 is and just write 1. If there's no 1, then it's just 0. Okay, so that means suddenly we are here. We're at 2 in our little chart. So that means the left side is completely ignored since it doesn't meet that condition. Okay, now we have 2, and we use the OR operation with 1. So 1 is represented like this, and the result is 3. So if we have the condition, if y is bigger than center y, then use OR operation with 1 on this result, and that result will then after be a 3, and this is exactly what we need. Okay, now a different example. Let's say x is big. This x is bigger than center x, but this does not apply. Okay, what happens here? Again, we will do the OR operation on 0 0, like because we have a 0 here, and our 2, and we end up with 2, and as you can see, that's it. That's our result, because this will never go through, and our 2 is here, and it's exactly what we want. Okay, so if you don't get it, think about it a little bit. I know it's a little complicated, but it is certainly a clean and efficient way of doing it, instead of typing million lines of if-else condition code. Note, you can also do the same thing. It's not the same thing, but you can use binary operations to calculate the new bounding boxes by using bitwise AND operation. But if you want, I can show you the method. I didn't want to do it here because I felt like it is a little bit overkill. But if you want to do it, if you want me to do it, then let me know. It is also very short code. It's maybe like 5 or 6 lines of code, and it actually scales better because we don't have to manually type in new cases if our new cases are needed. For example, in an Quadtree where you have 8 children in 3D space. Anyway, there's one more function that I want to show you. Actually, 2. One is very trivial. It's called draw border, and I'll just describe this. Draws this bounding box. As you can see, it is exactly what it does. It just draws this bounding box with the square, and that you saw earlier in our simulation. And half length here, and yeah, and one last function called contains position vector 2D. So during our code, our simulation, we check if a vector is inside that position, and or is inside that bounding box. If it's not, then we do something. So that's very important for us. And let's just say we got that lower equals center dot plus Okay, so what I'm doing right now is I'm describing 2 vectors, corner vectors, that are lower and upper. So this lower is just the lower left corner of our bounding box, and this upper is the upper right corner. And with this, we can just call return position dot greater or equal than lower, and position dot less or equal than upper, and this will returns true if position is inside the bounding box. Okay. Why does this work? This works because we have 2 corner vectors, lower left, upper right, and we just check if the position is greater than all values of our lower, then it's definitely bigger than lower, and it is inside, and it is less than upper. So that means it must be somewhere in the box. If not, then it's outside. Okay, so that's it for our bounding box class. I don't think that we have anything more to do. This is finished for now. Yes, I think that's it. There's no more things that we can add. And again, thanks guys for watching. This has been a little more complicated than it was until now, but I hope you guys understand it. And if you have any questions or any topics you want me to cover, then please let me know. Otherwise, I wish you a good day, and thanks for watching, and I'll see you in the next video. Bye bye.